Good morning. Hello, friends. Hope you all are safe and sound. Yes. So, in paper section, in paper first, section 1, what we have discussed yesterday is about free radicals. We have seen the different methods in reaction mechanism. What are the application of free radicals? And then how to generate the free radical, that also we have started. Okay, so generation of free radicals, uh, in that today also we will see the based on the peroxide and which the different peroxides are there. Right, so let's begin. I will start the presentation. And then we have to move towards the stability part, right? Stability of the peroxide. So we have seen in pericyclic we have used the two conditions, which is thermolysis and the photolysis method. Okay, means thermal and use of photon we can generate the peroxides. Okay, and in this photochemical reaction where we can use the peroxide to generate the free radical, and the one example which we have taken is this one. Okay, here you can see by homolytic fission, because yesterday we saw the both type of fission, which is homolytic fission and heterolytic fission as well. Okay, and you can see here the after the decarboxylation, you can get the stable this free radical. In this case, we have also learned one conditions, which is if this R is an alkyl group, the loss of CO2 is very fast. Okay, if it means here is methyl or propyl or like that. So if CO2 loss is very fast, means the stability is very difficult. Therefore, alkyl peroxide is generally avoided because highly reactive, and as they tend to be explosive type of reaction. Right? So there, and that explosive reaction is not good for our study. So what we have to do is, rather than this alkyl, we have to take aromatic type of substituent, and generally this benzyl peroxide use for the this generation, because this benzoyl peroxide has a half life of 1 hour at 90 degrees centigrade, and which is very useful as it selectively decomposes to benzoyl radicals below 150 degree centigrade. After 150 degree centigrade again, which is dangerous or which is not useful, we can say, right? So this part, and we'll see the another peroxides are there. Okay, see, write down this also. This is another peroxide initiator, DTBPO, and the name of DTBPO is ditertiary butyl peroxide. So write down the structure of this also, DTBPO, which is ditertiary butyl peroxide. See, again there is a homolytic fission in two places. Yes, and half life is 10 minutes at 70 degrees centigrade, which is too much, or which is sufficient for the reaction studies. And when there will be a decarboxylation, there will be generation of radicals, right? Or many times, what type of radicals you will get is methyl radical, our in final stage, and side product will be acetone, right? So this is the generation of radical from DTBPO, ditertiary butyl peroxide. Or we'll see the next one also. I think I have collected more than 4. Yes. See, this is again the famous initiator called AZO initiator, name is AIBN. Okay, AIBN means azo bis isobutyronitrile. You see, the actual structure is very simple, but name when you heard the first time you feel which is difficult, but this is very interesting structure. See, this is azo bis, two nitrogen are there, and butyronitrile. Okay, so isobutyronitrile. So 4 carbon, including cyanide, right? And cyanide we have to say here is nitrile. And if when there will be a fission, there will be a nitrogen molecule will go out, and there will be formation of this type of radical, and which is interconvertible. And why this is stable? See, there are some chances to stabilize it within the molecule due to this resonance. Okay, hope you understand that this arrow is used for the resonance purpose. Right? The same way we can write down like this. If we have this tin hydrogen, we can say tin hydrogen, uh, butyl tin hydrogen. Okay, so when there will be weak bond between tin and hydrogen, this radical will abstract this hydrogen, and there will be formation of this tin butyl radical. It means a combination of AIBN and tin butyl hydride is most popular radical initiation pathway in organic synthesis. Right? Whenever you will find the AIBN, you will find there another reagent, or this combination is very famous, like Ram Lakshman. Okay, the combination you will find always in our places. Okay, so hope you have written the structure of AIBN, how it can be generated in the stable radical. The half-life is very sufficient, or which is stable, and there is always found the combination between tin hydride, tributyl hydride. Right? So this is the third one. We'll see the fourth one. Some radical initiator are organometallic. Okay, organometallic means there will be a bond between carbon and metal. So carbon metal bonds have low BDE and are easily homolyzed into radicals. See, this is like, hope you remember the trimethylsilane. So this is TMS, which we use in NMR spectroscopy. So like that, this is tetramethyl lead. Okay, and when you will heat it, you will find some radicals like methyl radicals in that. Okay, so this is the another organometallic initiator that we can get the free radical very easily. Okay, next formation of Grignard reagents. This is very famous and familiar to all of us. Yes, when the aryl bromide react with magnesium, there will be a formation of Grignard reagent, and in this intermediate state there will be free radical formation. Okay, so this aryl bromide, there will be a homolytic fission and you will get the radical. Obviously this radical is quite unstable, and immediately you will get the this Grignard reagent, and this Grignard reagent is very active or reactive. All right, so lot of condition we have to use when we generate this Grignard type of reaction. Okay, next, can we move? Yes. Using this radical, or can we done some reactions, electron transfer process. One reaction is Kolb reaction. There you can see this electrochemical oxidation. There acetic acid. There you will find one electron on oxidation. Means one electron will remove, and there will be formation of radical. This radical will get transformed, and you will get the R radical after decarboxylation, right? And R radical get converted into the RR, means higher alkane. Okay, this is the Kolb reaction. This type of reaction is reaction which is removal of carbon. Means whatever starting material is there, and the product you will find one carbon less compared to the first because of decarboxylation. Next, there is another reaction. See, this is single electron transfer reaction. What will happen here? Again, this is the very famous when alkyl halide react with one metal. Okay, or metal initiator. What this metal used to do is, metal which is already positive will give one electron here and it will go out. Okay, so when one electron will add on this substrate, there will be this kind of possibility. Okay, and then there will be a fission and you will get the radical. We'll take the example directly, which is, suppose this is the derivative of imidazole. Okay, hope you understand the structure of imidazole. Okay, the bromo derivative, and one side bromo, another side methyl. These are the substituents on imidazole. Okay, N-methyl imidazole, like this. There you can see there is ammonia and sodium and ammonia. So in the presence of ammonia, what sodium used to do is, sodium will donate one electron to this imidazole and it will go out like sodium plus. Okay, obviously the sodium has given one electron in this reaction, and what you will get is the radical anion. Okay, and because this extra electron on this imidazole, there will be a homolytic fission in between carbon and bromine, and you will get the sigma imidazolyl radical. Okay, and which is quite stable. So in such kind of reaction, which is single electron transfer reaction, the initiation using a metal is ammonia, and the example is aromatic halide or aliphatic halide. Anyway, then electron transfer from the ammonia, and what you will get is this one. Okay, so this is another generation of radical reaction, which is single electron transfer reaction. There are again some reactions. There you can see the generation of radicals. Okay, one reaction is Fenton reaction. Then this is a very famous reaction related to the iron. Okay, when hydrogen peroxide react with iron having two valency. Okay, the oxidation state of iron is 2, and obviously these 2 will get converted into 3 because will donate one electron to the hydrogen peroxide, and the hydrogen peroxide will become, or it will initiate and there will be a formation of OH radical, right? How it will happen? This peroxide was there, and there will be extra electron from this penton, okay, or iron, right? And then one OH will become a minus because of extra electron, and then uh, another OH will become as a OH radical. So this is again Penton reaction is good to generate the free radical. Right, guys? Yes. Also, the tertiary butyl peroxide. Tertiary butyl peroxide. Again, it will initiate with the penton, which is Fe2 plus. Fe2 plus will get converted into Fe3 plus. It will donate one electron to tertiary butyl peroxide, and there will be a fission. Okay, and what type of radical you will generate? Tertiary butyl oxide radical, right? So this is another method to generate free radical. So all the radical initiation pathways so far discussed give very reactive, short-lived, which are useful in synthesis. Okay, these all radical which is useful in the organic synthesis. Can move? Yes. Which is stable and persistent radical. See, so this is actually maybe stable is kinetically. Stable means kinetically. See, this is the starting material. Triphenyl काय म्हणूया त्याला? This is methyl chloride. Triphenyl methyl chloride. Okay, triphenyl methyl chloride get react with silver radical, and this silver radical will get convert into this triphenyl methyl radical. Triphenyl methyl radical, and this triphenyl methyl radical is quite stable because there are chances of resonance, because this radical will go towards this ring, then afterwards this ring, then afterwards this ring. So there are a lot of chances of resonance. Okay, this radical you will find sometimes here, sometimes here, sometimes here. Okay, so there are lot of chances to stabilize it. Okay, so which is quite stable, we can say, which is kinetically stable radical. Okay, and this triphenyl methyl radical may be dimerized. There are chances of dimerization because these two molecules get attached each other, and you will find this type of structure. Okay, or another possibility is like this, because these two molecules will get attached and you will find like this structure. Right, so there are also chances. So due to the steric shielding is more important than resonance stabilization of the radical centers. So the kinetically stabilized radical and having half-life is 0.1 second. Okay, 0.1 second. So this radical, which is triphenyl methyl radical, is quite stable. Next, another very stable radicals and having half-life is some years. Oh my God. Okay, so we can easily handle it, right? Like other chemicals, like you have a radical initiator and you have used like salt, right? So this much easy we can handle this type of initiator. See, thermodynamically, thermodynamic stabilization is most important because of some temperature, or at room temperature also we can store it. These radicals can be stored on the bench and handled like other ordinary chemicals without any adverse reaction in air or light, right? So this is the name DPPH. Very nice. So diphenylpicaryl hydrazine radical. Diphenylpicaryl hydrazine radical, which is DPPH. So write down the structure, and this is most stable or very stable radicals and having half-life is of years, right? This is one thing, DPPH. Another one is often very colorful compounds like nitroxide. So see, there are two structures, one is TEMPO and other is TMIO, which is colorful radical. One is having TEMPO having color is red and TMIO having color is orange yellow. The name are like the TEMPO is 2266 tetramethyl piperidinilyl oxy. Okay, like that, and this is the derivative of imidazole. Okay, so both are the quite stable, which is we can say which is thermodynamically stable initiators, right? And having the nitroxide group present there, and which are the colorful compounds, right? So I think almost 10 compounds which we have learned today, the how to generate the radicals that we have learned, and which is the stable, because the stability is also important, and the thermodynamic stables compounds which is available in the market, that also we have learned today. Okay, and next part in next session we will learn about the stability of the these free radicals. Okay, so what factors are important on the stability or thermodynamic stability, or means why this nitroxide is stable, right? Why DPPH is quite stable, having half life is some years. Okay, so that part we will see on the next session. Right. So thank you guys, and see you in the next session.